Chapter 6 Thermochemistry Energy Flow and Chemical Change. In this chapter, we'll first look at forms of energies and their interconversion. We'll introduce enthalpy to study heat under constant pressure, and we'll use calorimetry to measure the heat of chemical or physical change. We'll study stoichiometry of thermochemical equations, Hess's law to find the enthalpies of chemical any reactions, and the standard enthalpies of reactions. This chapter is about thermodynamics, which is the study of energy and its transformations. Thermochemistry is a branch of thermodynamics that deals with the heat involved in chemical and physical changes. And you will see that when energy is transferred from one object to another, it appears as work or heat. In thermodynamics, we define the system as the part of the universe we are focusing on. In this case, is the contents of the reaction flask. Everything else is the surrounding, including the flask itself. A meaningful study of any transfer of energy requires that we first clearly define both the system and its surroundings. The universe is the sum of the system and its surroundings. We mentioned in previous chapters potential energy and kinetic energy. Potential energy is related to position. Potential energy for gravity, for example, is mgh. H is the height. For molecules, potential energy is related to bonding. Kinetic energy is about motion. In physics, it's half mv squared. V is the speed. The sum of the potential energy and the kinetic energy is called the internal energy of a system, which is represented by E. The internal energy of a system can change, which appears as two forms, heat and work. Q represents heat, W represents work. W delta means change, so the internal energy of a system can change, which appear as heat or work or both. When internal energy of a system changes, the energy of surrounding must change so that the total energy of the universe remains constant. A change in the energy of a system must be accompanied by an equal and opposite change in the energy of the surrounding, so they add together give you a constant energy of the universe. And this is called the conservation of energy, or the first law of thermodynamics. This diagram shows the transfer of internal energy between a system and its surrounding. On the left side, the final energy of the system is lower than the initial energy. So the energy decrease. The change of the internal energy is the final minus initial. So if initial is 5 kilojoule, the final is 2. Okay, when you use 2 minus 5, which give you negative 3. So when the energy of the system decrease, the change of internal energy is negative. Where does the energy go? It goes to the surrounding. So when energy of the system decrease, the energy is released to the surrounding. On the right side, the final energy is higher than the initial energy. So for example, in this case, from 2 goes to 5. So we use 5 final minus initial. This gives you positive 3. So when energy of the system increase, the change delta E is positive. Where does the energy come from? Well, the energy comes from surrounding. So when energy of the system increase, the system absorbs energy from surrounding. Let's ignore work and consider heat as the only source of energy change. And suppose the hot water is our system, and the beaker holding it and the rest of the lab are the surroundings. The water transfers energy as heat outward until temperature of the water and the surroundings are equal. Since heat flows out of the system, the final energy of the system is less than the initial energy. So this final is less than the initial, and delta E is negative. In this case, the energy change takes form of heat, so Q is negative. On the right side, the system consists of ice and water, and the surroundings transfer energy as heat into the system, and once again until ice melts and the temperature of water and the surroundings becomes equal. In this case, heat flows in, so the final energy of the system is higher than the initial energy. And so in this case, delta E is positive. And heat is the form of energy change, and therefore Q is positive. So when energy is absorbed as heat by the system, Q is positive. And when energy is released to the surrounding as heat, Q is negative. Let's ignore heat and consider work as the only form of energy change. Our system contains hydrochloric acid and zinc. These two reactants react to form zinc chloride and hydrogen gas. And when hydrogen gas is formed, it pushes back the piston as it expands, and therefore energy is transferred as work done by the system on the surroundings. Since the system releases energy as work done by it, the final energy of the system is less than the initial energy, and therefore delta E is negative. Okay, because the system loses energy through work, and since there is no heat, so work is negative. So when energy is released as work, W is negative. Suppose that after reaction is over, we increase the pressure of the surrounding so that the piston moves in, compressing the hydrogen gas into a smaller volume. So in this case, energy is transferred as work done by the surrounding on the system. So system absorbs energy as work done on it. So the final energy, therefore, increase is greater than the initial energy. Okay, because it absorbs energy as work done on it by the surrounding. And in this case, delta E is positive. And since no heat, so work is positive. And therefore, when energy is absorbed as work from surrounding, the work is positive. In summary, when system absorb heat from surrounding, system gain energy, heat is positive. When system release heat to the surrounding, system lose energy, heat is negative. When work is done by surrounding on system, system gain energy, work is positive. When work is done by the system on surrounding, system lose energy, work is negative. Suppose the system absorb heat from surrounding, that give you a positive Q. At the same time, surrounding do work on system give you a positive W. The combination of these two increase internal energy give you a positive delta E. On the other hand, if the system release heat to the surrounding, give you a negative Q. At the same time, system do work on surrounding, give you a negative W. The combination of these two decrease internal energy, give you a negative delta E. Suppose the system absorb heat, a positive Q, but at the same time, system do work on surrounding, give you a negative W. Then the internal energy may increase, may decrease, depends on the size of Q and W. Similarly, if a system release heat, but the surrounding do work on system, positive W, then again, the sign of delta E depends on the size of Q and W. We already mentioned that the total energy of the universe is constant, which is called the first law of thermodynamics. This law states that energy is conserved. It can neither be created nor destroyed, but energy can be transferred in the form of heat or work. If systems change energy, the surrounding must change in the opposite way, so they combine together. Delta E of the universe is 0, so that the energy of the universe remains constant. The SI unit of energy is the joule. In physics, work is calculated by force times distance, and the force is calculated by mass times acceleration. The unit of mass is kilogram. For acceleration is meter per second squared, and distance is meter. So the combination of these three give you kilogram meter square per second square. 1 joule equals 1 kilogram meter square per second squared. The calorie is once defined as the quantity of energy needed to raise the temperature of 1 gram of water by 1 degree. 1 calorie equals 4.184 joule. The British thermal unit, BTU, is often used to rate appliance. 1 BTU is equivalent to 1055 joule. Sample problem 6.1. When gasoline burns in a car engine, the heat released causes the gaseous products CO2 and water to expand, which pushes the pistons outward. Excess heat is removed by the radiator. If the expanding gases do 451 joule of work on the pistons and the system releases 325 joule to the surroundings as heat, calculate the change in internal energy in joule, kilojoule, and kilocalorie. So first we need to know what is system, what is surrounding. The system is the reactants and the products, and the surroundings are the pistons, the radiator, and the rest of the car. Since heat is released by the system, so Q is negative. So in this case, Q is negative 325 joule. Since work is done by the system to push the pistons outward, so work is negative. So W is negative 451 joule. We have the equation delta E, the internal energy change, is the sum of heat and work. So we combine heat and work together, give you negative 776 joule. That means the internal energy of the system decreased by 776 joule. To convert to kilojoule, okay, we divide by 1000. So we use this as a conversion factor, 1 kilojoule, 1000 joule. Okay, and that gives you kilojoule, negative 0.776. To convert to kilocalorie, okay, we first change to calorie, because we have 1 calorie 4.184 joule, so that gives you calorie, and then change to kilocalorie, 1 calorie, kilocalorie 1000 calorie. Okay, so you divide by 1000. So that gives you negative 0.185 kilocalorie. Internal energy is called a state function. A property depends only on the current state of the system, not on the path the system takes to reach that state. Suppose we have a system containing octane and oxygen as initial state. These two reactants react to form a product, CO2 and water, as its final state. The reaction produces heat, and heat goes to the surrounding, and therefore the internal energy decreases. So delta U equals Q plus W. Okay, if the reaction releases heat, so without doing any work, so W is 0, and the Q goes to surrounding, so it's negative, and delta E is also negative, so energy goes down. Now, if we put these two reactants inside a car engine and let them burn inside the car engine, 30% of energy will be transferred as work. The rest becomes heat to warm the car and exhaust the gas and the surrounding. So delta E now equals Q plus W, but W is not 0. Okay? Now in both process 1 and 2, they start with the same reactants and they end up with the same product. So the initial state, final state are the same. And because internal energy is a state function, so delta E are the same. So delta E1, delta E2, they are the same. Okay, because they start with the same initial state and end up with the same final state. But the Q are different. So Q1, Q2 are different. W1, W2 are different. For example, W1, W2, well, W1 is 0 and W2 is not. Okay, but when you combine Q and W together, they give you same delta E, because E is a state function, only depends on initial and the final state. Q and W are not a state function. They depend on path. How do we calculate work? Suppose we have a cylinder with a movable wall under constant external pressure. And if we let the system expand to push back the atmosphere with volume change delta V, the system to work to the surrounding. And the work is called pressure volume work, or PV work. And the equation to calculate is negative pressure times volume change. Negative sign is consistent with the chemistry convention that if the system to work to the surrounding, work should be negative. What if work is done by surrounding on system? Suppose surrounding push the piston down to reduce the volume. Okay, so in this case, the delta V is negative. Okay, so for example, here initially volume is 5, final state is 2. So you go this way, and the delta V is 2 minus 5 is negative 3. Okay, so according to this equation, negative pressure times a negative volume change, and that gives you positive 3 times pressure. And this is again consistent with the chemistry convention that if work is done by surrounding on system, work should be positive. Sample problem 6.2. A reaction takes place in a container with a piston cylinder assembly at a constant temperature produce a gas, and the volume increases from 125 milliliter to 652 milliliter against the external pressure of 988 torr. Calculate work done. The equation to calculate work is pressure, negative pressure times volume change. So the volume change from, so this is the initial volume, this is the final volume. So delta V can be calculated by V2 minus V1. Now, milliliter needs to be converted to liter, okay? And the pressure given 988 torr, so torr needs to be converted to atmosphere. Okay, so first convert milliliter to liter and torr to atmosphere. And then using this equation to calculate work, the unit will be atmosphere liter. And using this as a conversion factor, we can change it to joule. Okay, so first calculate delta V, use final minus initial. Final is 652, initial 125. So the volume change is positive, means it expand, increase volume. And then change milliliter to liter. Okay, 1 liter, 1000 milliliter. All right, so that give you, so milliliter cancel, give you 0.527 liter. And then pressure, okay, torr becomes atmosphere, so 1 atmosphere, 760 torr. So cancel torr, give you atmosphere. And then using the equation negative pressure times volume change. So that's the pressure, that's the volume, and don't forget the negative sign here, and that give you negative 0.685 unit is atmosphere liter. That's not joule. So to convert to joule, use the conversion factor. 1 atmosphere liter equals 101.3 joule. So cancel atmosphere liter, give you negative 69.4 joule. Okay, a negative sign indicates the work is done by the system on surrounding. So because it's expand, so it does work on the surrounding. You already know that internal energy is a state function that only depends on states, not the path. We now introduce another state function called enthalpy, represented by H. So enthalpy is defined as the sum of internal energy E plus the product of pressure times volume. So H equals E plus PV. So the change of enthalpy should be the change of internal energy and the change of PV. Delta means the change. So the change of the left side enthalpy is the change of the right side, which is the internal energy and the product of PV. So in general, if we want to know the internal energy change, we have to know heat and work. Now, under constant pressure, we already know work can be calculated by negative pressure times the volume change. So delta E now is heat minus P times delta V. And if it's a pressure constant, then the change of product PV can be written as only volume change times pressure, because pressure does not change. So the change of product PV is just P times delta V. And so you can see this one is negative, one is positive. They cancel each other. And so we have delta H equals Q. Now here P means constant pressure. So this heat is under constant pressure. And this leads to a very important conclusion, and that is the change in enthalpy equals the heat absorbed or released at a constant pressure. So if we want to know how much heat involved in the reaction or any process, we just need to measure the enthalpy change. Knowing the enthalpy change of a system tells us a lot about its energy change as well. And this is because in most cases, the change of PV is a very small number, approximately 0, and therefore delta H equals delta E. Here are some examples. For the reactions that do not involve gases, only involve solid or liquid. Because solid liquid, volume do not change. So because volume doesn't change, so the PV product doesn't change. That's 0. And therefore delta H equals delta E. Now for some reactions, the reaction involves gases, but the total amount of gases do not change. One example is nitrogen, oxygen, so they are all gases, forms nitrogen monoxide. Okay, so you can see the reactants, 1 mole nitrogen, 1 mole oxygen, that's 2 moles, and the product also 2 moles. So from 2 moles to 2 moles, the number of moles do not change. Okay, and therefore the product PV doesn't change, it's 0. Okay, now for some reactions which involve gases, the total moles of gas changes. However, the QP may be not much larger than P delta V. One example is hydrogen plus oxygen forms water. Okay, and for this reaction, the delta PV, so delta PV change is about negative 2.5 kilojoule, and the QP or delta H enthalpy change is negative 483.6 kilojoule. Okay, so according to the definition, enthalpy equals energy plus PV. So delta H, which is negative 483.6, and equals delta E plus delta PV, and delta PV is negative 2.5 kJ, so kilojoule. And so if you use this equation, you can calculate delta E can be negative 481.1 kilojoule. Okay, so delta H is negative 483 and delta E negative 481. So they are approximately the same because delta PV is much smaller than delta H. So under this condition, for these reactions, enthalpy also give you a good indication of the energy change. Under constant pressure, enthalpy change equals heat, and therefore the sign of enthalpy is the same as the sign of heat. Now suppose we have a system containing methane and oxygen, 2 reactants as the initial state, and the product CO2 water as the final state. So this process is an exothermic process, means the reaction releases heat. So heat goes out from the system to the surrounding. We can use the heat as a product. Okay, so the reactants forms CO2 and water, but also heat. Okay, because heat goes out as a product. Now, because heat is released, and therefore the enthalpy decreases, so it goes down, and delta H is negative. So when heat is released, heat is negative, and the enthalpy goes down. So enthalpy delta H is also negative. On the right side shows ice, solid water melt to form liquid water. So ice is the initial state, liquid water is the final state. And when ice melts, it absorbs heat from surrounding to the system. And so we can write heat as a reactant. So water, ice plus heat. Okay, when the system absorbs heat, okay, we can write as a reactant to form liquid water. Okay, so this process absorbs heat, and therefore enthalpy increase. Delta H is positive. Okay, so when heat is absorbed, heat is positive, and the enthalpy change is also positive. Sample problem 6.3. In each of following cases, determine the sign of delta H. State whether the reaction is exothermic or endothermic, and draw an enthalpy diagram. In the first reaction, the reactants are hydrogen gas, oxygen gas, and product is water plus heat. So in this case, heat is as a product. That means heat is released from system to surrounding, and therefore the reaction must be an exothermic reaction. For exothermic reaction, the enthalpy decrease, and so reactants initial enthalpy must be higher than the final enthalpy. Okay, so this is initial. Okay, now in second reaction, heat as a reactant to react with water forms liquid water forms gas water. So if heat serves as a reactant, then the enthalpy increase. Okay, so this is an endothermic. The reaction absorbs heat, and so it's an endothermic reaction. And the reactant's initial state, okay, that's the initial, and plus heat, so that's the heat, and it goes to the final state. Okay, so here are the answer keys. For A, heat is a product, and so delta H is negative. It's an exothermic reaction, and so this is the reactants release heat to the surrounding to form the product. And for the second reaction, heat as a reactant, and so the reaction is endothermic, absorb heat. So this is the reactants absorb heat becomes product. You know from everyday experience that the more you heat an object, the higher its temperature, and the more you cool it, the lower the temperature. In other words, the quantity of heat absorbed or released, which is Q, is proportional to its temperature change. The heat is also proportional to the amount of substance. So M is the mass of the substance. So Q should be proportional to mass and temperature change times a constant C called the specific heat capacity. The specific heat capacity of a substance is the quantity of heat required to change temperature of 1 gram of the substance by 1 Kelvin. So if we know the specific heat capacity C, and we know mass, and if we can measure the temperature change, then we can calculate how much heat involved in a specific process. Now, if we can measure the heat, on the other hand, and the temperature change, then we can calculate the heat capacity, which is Q divided by M and the temperature change. So the mass, temperature change, heat. Okay, we can calculate the heat capacity. And note that in this equation, delta T is the temperature change, is the final minus initial. So suppose initial temperature is 20 degree, okay, so Kelvin, which goes to 40 Kelvin. So the delta T is final 40 minus 20, which give you 20, which is a positive number. So Q will be positive. A positive Q means the process absorbs heat. The object absorbs heat. So when the substance absorbs heat, temperature goes up. So from 20 to 40. Now, on the other hand, if the process goes from 50 to 30, okay, then delta T equals final, which is in this case is smaller than initial, and that gives you a negative number. Okay, 20. So a negative number put into the equation, Q will be negative. A negative Q means the process release heat. So when the process release heat, the temperature goes down. So from 50 to 30, for example. This table shows specific heat capacities of some elements, compounds, and materials. Water has a specific heat capacity exactly 1 calorie per gram Kelvin. 1 calorie equals 4.184 joule, and therefore the specific heat capacity for water is 4.184 joule per gram per Kelvin. Sample problem 6.4. A layer of copper welded to the bottom of a skillet weighs 125 grams. How much heat is needed to raise the temperature of the copper layer from 25 degrees to 300 degrees? So the question is how much heat, and heat can be calculated by the specific heat capacity times mass times temperature change. Specific heat can be found in table 6.2, and the mass is 125 grams. Delta T, the temperature change from 25 degrees to 300 degrees. So using final minus initial, we can get delta T. And the heat capacity is found for copper from the table should be 0.387. We first calculate delta T, final minus initial. 300 minus 25 give you 275. So heat is heat capacity, mass, and temperature change. And that gives you 1.33 times 10 to the 4th power joule. During the calculation, you may wonder why 275 Celsius equals 275 Kelvin. Well, first, let's convert Celsius to Kelvin. Okay, so 300 becomes 300 plus 273.15. So that gives you Kelvin. So that's the final. Minus initial is 25 plus 273.15. And you can see here, final, initial both has 273. They cancel each other. So what you end up with, again, 300 minus 25. So the conclusion is, when you calculate delta T, even though the unit may be Celsius, the number gives you the same as Kelvin. So you get 275 Celsius that equal to 275 Kelvin. Okay, remember this is only true for delta T, not at temperature itself. It's the temperature change. Calorimeter is used to measure heat in a process. There are two types of calorimeters: constant pressure, constant volume. Coffee cup calorimeter is an example of a constant pressure calorimeter. And this calorimeter uses styrofoam cup as its container and a cork stopper for the cap. This ensures that the system is insulated, so heat cannot escape or cannot go in. A stirrup is used to make sure the temperature of the water bath is uniform, and a thermometer to measure the temperature. This simple apparatus can be used to find the heat of an aqueous reaction. The heat accompanies the dissolving of a salt, or even the specific heat capacity of a solid that does not react or dissolve in water. Suppose we want to measure heat capacity of a solid. We first take a small amount of the solid and measure the mass M1 of the solid and heat it to a certain temperature T1, and then we place the solid inside the water bath. Now you expect the temperature of the solid goes down, and at the same time water temperature goes up. The heat released by this solid should equal to the heat absorbed by water. So heat released by the solid is M1 C1 heat capacity of the solid times mass times the temperature change should equal to the heat absorbed by water, which is C2, that's the heat capacity of water, times M2, that's the water mass of the water bath, and times the temperature change for the water bath. And so these two should equal, but opposite sign. So you add a negative sign, okay? Because one release heat, one absorb heat. So they have opposite sign. And therefore, we can calculate C1, the heat capacity of the solid, should equals to negative heat capacity of water times the mass of water in the water bath times the temperature change of the water bath, divided by the mass of the solid times the temperature change of the solid. And that gives you the heat capacity of the unknown solid. Sample problem 6.5. You heat 22.05 grams of a solid in a test tube to 100 degrees, and then add the solid to 50 grams of water in a coffee cup calorimeter. The water temperature changes from 21.1 to 28.49 degrees. Find the specific heat capacity of the solid. So the initial solid temperature is 100, and the initial temperature of water is 25. So the temperature of solid is much higher, and the solid temperature will go down, and the temperature of water will go up. And the final temperature 28. This is the final temperature for water, but also for the solid. So that's the temperature when they are in equilibrium. Okay, so first we can calculate delta T. So for delta T, temperature change for water, final is 28.49 minus 25.10. So that gives you 3.39 Celsius. As we mentioned before, delta T in Celsius is the same as in Kelvin. So that gives you 3.39 Kelvin. Similarly, the change for a solid is final, which is also 28.49 minus 100 give you negative 71.51 Kelvin. Now we use the equation Q, the heat released by the solid, should equal to the heat absorbed by water. Okay, and they are in opposite sign, so one has a negative, one is positive. And using this equation, as we shown in the last slide, we can derive this equation. The heat capacity of solid should equals to the negative heat capacity of water, mass of water, temperature change of water, mass of solid, temperature change of solid. The heat capacity of water is 4.184 joule per gram per Kelvin, and the mass is 50 grams as in the question, and the temperature change is here 3.39, and the solid mass 22.05 gram, and the temperature change is negative 71.51, and that gives you 0.45 joule per gram per Kelvin. Note that you have a negative sign here, you also have a negative sign here, and that gives you a positive heat capacity. If you calculate heat capacity to be a negative number, then there must be something wrong. Sample problem 6.6. You place 50 ml of 0.5 molarity sodium hydroxide in a coffee cup calorimeter at 25 degrees, and add 25 ml of 0.5 molarity HCl also at 25 degrees. After stirring, the final temperature is 27.21 degrees. Question A. Calculate the heat of the solution in joule. So this is about a acid-base reaction. The base is sodium hydroxide. We have volume, we have molarity, and that gives you number of moles. We also have acid, volume, molarity. So we have number of moles of the acid. Okay. Okay, now note that both at 25 degrees. So if you mix together, the temperature shouldn't change. But after stirring, the temperature becomes 27. So temperature increase. This increase must due to the chemical reaction. So from 25 to 27. So the chemical reaction must be an exothermic reaction, release heat to increase the temperature. And also note that for a solution of acid base, the solute is very small, mainly just water. So basically, you have 50 milliliter of water plus 25 milliliter of water, and the water temperature change from 25 to 27. So the water absorb heat from chemical reaction, increase temperature about 2 degrees. Okay, so from this you can calculate the heat. So the heat water absorbed should be the mass, the heat capacity of water times mass times delta T. Okay, so mass, we have volume, we have 50 milliliter plus 25 milliliter, and we have the density, so we can calculate the mass. All right, so density for water is 1 gram per milliliter. Okay, and the heat capacity is 4.184, and the temperature change from 25 to 27. So we can calculate heat. So first, the mass is, we calculate volume added together. Okay, two solutions added together, and times gravity, the density, and that give you 75 gram. So two solutions added together, total 75 gram of water. And the temperature change is 2.21 Kelvin. So the heat can be calculated. So that's the heat capacity of water times mass times temperature change, and that gives you 693 joule. In question B, it asks you to calculate the change in enthalpy of the reaction. Well, because the process is constant pressure, so the enthalpy change is the heat. So you're asked to calculate the heat of the reaction. Now we already calculate the heat of the heat absorbed by water. So these two should equal, but in opposite sign, because reaction release heat and solution absorb heat. So the heat of the reaction must be negative of 693 joule. Now if you notice that the unit is a kilojoule per mole of water, and therefore you need to convert to kilojoule, but also you need to divide by number of moles of water formed during the reaction. Okay, because it's an acid-base reaction, it forms water. So whenever it forms 1 mole of water, how much heat is released? That's what is asked for. Okay, so to calculate the amount, the number of moles water formed during the reaction, we need to write the balanced equation. And also, because we know both the acid and the base, one of them must be a limiting reactant. And therefore, we need to find the limiting reactant. And then, using the limiting reactant, we find how many moles water formed. And then use this one to divide by the number of moles water, give you every mole of water, how much heat is released. We first write the balanced equation. HCl, sodium hydroxide, forms water, and sodium chloride, and the ratio is 1:1 reactants, and the product is also 1. Okay, the number of moles of hydrochloric acid is its volume times molarity, give you 0.0125. Okay, if you use hydrochloric acid to calculate the product, because the ratio is 1:1, so that gives you 0.0125 moles of water. Okay, now the number of moles of sodium hydroxide is the volume of sodium hydroxide times molarity, give you 0.025 moles sodium hydroxide. Using sodium hydroxide, you can calculate the number of moles of water will be 0.025 moles of water. And because this is smaller, so hydrochloric acid should be the limiting reactant, and this is the number of moles of water that will be formed during the reaction. Okay, and therefore we can use the heat, okay, is the negative of the heat of the solution divided by this number of moles. Now this is in joule, and therefore, so after you calculate joules divided by moles, and then you divide by 1000, give you unit in kilojoule. So that give you -5 delta H is -5 kilojoule per mole. A second type of calorimeter is called a constant volume calorimeter. An example is a bomb calorimeter. So a reactor is placed inside a water bath. So this is water bath. And outside there are insulation layers to ensure heat cannot escape from calorimeter. The key of this device is the reactor made of stainless steel, so volume doesn't change. It's a constant volume. This device is commonly used to measure heat of combustion reactions, usually involving fuels or foods. Okay, so for example, an organic sample is placed inside this reactor, full of oxygen gas. Electric source is used to ignite the reaction, and the combustion reaction is exothermic, so heat goes into water bath, increase temperature. So by measuring the temperature change, we can calculate the heat. So heat of reaction, okay, so heat of reaction should equal to the negative heat of calorimeter. Okay, so you have a negative sign because the reaction release heat and the calorimeter absorb heat. Calorimeter here includes mainly the water bath, but also the reactor itself and the stereo, the thermometer. Okay, to calculate the heat of calorimeter, we use the heat capacity of calorimeter times the mass times temperature change. Okay, now calorimeter, the heat capacity usually is in the unit of joule per gram per Kelvin. Okay, now for a certain calorimeter, the water amount is fixed. For example, every time we use exactly 2000 milliliter, okay, 2000 milliliter. So every time we use the same amount of water, and therefore the mass it doesn't change. And therefore, to simplify this, we can combine these two together and find a new heat capacity. So now we use only heat capacity times delta T instead of heat capacity times mass, because mass doesn't change. But this heat capacity unit should be joule per Kelvin. And there's no gram because you combine together. So gram and the mass gram cancel each other. So you have a new heat capacity of calorimeter with unit joule per Kelvin, and then you times temperature change, and that just gives you joule. Okay, now the calorimeter heat capacity can be found by experiment. So for example, you use a known compound, you know the heat, okay, and then you calculate, you measure the temperature change, then you can find the heat capacity, and that's called the calibration. Okay, now for a fixed calorimeter, the heat capacity doesn't change. So you use a known compound, you find the heat capacity, and then you use the same heat capacity to calculate an unknown compound. So for example, you use you have an unknown compound, you measure a temperature change. You use the calibrated heat capacity times temperature change, you find the heat of the calorimeter, which equals the negative of heat of the reaction. Okay, so by measuring temperature change, you calculate the heat of the reaction of an unknown compound. Now, because it's a constant volume, so delta V doesn't change. So delta V is 0, and therefore P times delta V is 0. That means there's no work, and so delta E equals Q plus W, but W is 0 in a constant volume process, and therefore delta E is just the Q. So by measuring Q, we are actually measuring the internal energy change. And therefore, in a constant volume calorimeter, by measuring the delta T, we can calculate the internal energy change for a chemical reaction. Sample problem 6.7. Oxyacetylene torches produce such high temperatures that they are often used to weld and cut metals. When 2.5 grams of acetylene is burned in a bomb calorimeter with a heat capacity 10.85 kJ per Kelvin, the temperature increased from 23.488 to 34.988 Celsius. What is the internal energy change for the combustion reaction? As we explained in the last slide, for a bomb calorimeter, it's a constant volume process. Internal energy change is the heat of the reaction. And the heat of the reaction is the negative of heat of the calorimeter. And the calorimeter heat is calculated by heat capacity of the calorimeter times the temperature change. Here, heat capacity is in kilojoule per Kelvin. Alright, so 10.85 kilojoule per Kelvin, and we need to know the temperature change. So here from 23.488 to 34.988. So the delta T can be calculated, and delta T here temperature change is 11.5 Kelvin. Alright, so heat can be calculated. So the calorimeter heat is the calorimeter heat capacity times temperature change, and that gives you 124.8 kilojoule. Okay, now it asks you the internal energy of the reaction, which is the heat of the reaction, and this is the heat of the calorimeter. So heat of reaction should be the negative of this one, and also ask you kilojoule per mole. All right, we know grams, so first we use negative 124.8 kilojoule, and that's the heat of a reaction, divided by grams, so that's kilojoule per gram, and then use molar mass. So 1 mole acetylene, 26.04 grams. So this way we cancel grams, we get per mole. Okay, and so that gives you 1.3 times 10 to the third power kilojoule per mole of acetylene. You are familiar with the balanced equation as a stoichiometry to calculate between reactants and product. A thermochemical equation is a balanced equation that includes enthalpy change. The sign of enthalpy indicates whether reaction is exothermic or endothermic. A positive delta H is endothermic, a negative, which means exothermic. The magnitude of delta H is proportional to the amount of substance, so delta H of 2 moles of substance should be twice of the delta H of 1 mole of the substance. And the value of delta H can be used in a calculation in the same way as a mole ratio. So in a balanced equation, we can convert between substance A and substance B to calculate the number of moles. And now in a thermal equation, we add enthalpy so that we can calculate the heat absorbed or released during the reaction. Sample problem 6.8. The major source of aluminum in the world is bauxite, which is mostly aluminum oxide. Its thermal decomposition can be written as aluminum oxide decomposed into aluminum and oxygen gas. For this reaction, the enthalpy change is 1,676 kilojoule. If aluminum is produced in this way, how many grams of aluminum can form when 1000 kilojoule of heat is transferred. So if we look at the balanced equation, and we know that 1 mole of aluminum oxide is equivalent to 2 moles of aluminum and 3/2 moles of oxygen. And now the thermal equation tells us that there's an enthalpy 1676 kilojoule that is equivalent to this amount of substance. In other words, 2 moles of aluminum is equivalent to 1676 kilojoule of heat. Okay, so the question is, how many grams of aluminum, okay, can be formed by 1000 kilojoule of heat? Okay, so we can use this equivalence as a conversion factor, and so 2 moles aluminum is equivalent to 1676 kilojoule, and we start with this heat. Using this conversion factor, we can calculate how many moles of aluminum first. Okay, from moles of aluminum, we can calculate the grams of aluminum. Okay, so here we start with the heat that is transferred, and we use this conversion factor. 2 moles of aluminum is equivalent to 1676 kilojoule. So kilojoule cancel, give you moles of aluminum. And then use molar mass. So 1 mole aluminum, 26.98 gram aluminum. So moles cancel, give you grams. So the final answer is 32.2 gram aluminum. If we have a chemical reaction, the reactant is A and the product is P, and we want to find the enthalpy change for this reaction. Okay, now from A to P, there may be a different path. So A actually can go to first form B, and then B goes to C, and then C goes to P. So this is a different path. Now we know this second path, the enthalpy change for each step. So delta H1 is known, delta H2 is known, delta H3 is also known. Okay, so can we figure out the enthalpy for the overall reaction from A to P using these individual enthalpies? The answer is yes, because enthalpy is a state function. Okay, state function means the enthalpy change only depends on the initial state, final state. It doesn't matter how it goes there. So the first path directly go from initial to final, and the second path go step by step, so different path. But they start from the same initial state. They end up with the same final state, and therefore the delta H should be the same. So the second path, the first path delta H should equal to the second path, which is delta H1 plus delta H2 plus delta H3. Okay, now this is only true for state function. So if we want to calculate the work, then the work for this first path should not equal to the delta W1, W2, W3. W1 plus W2, W3. Okay, so this add together shouldn't equal, because work is not a state function. It depends on path. If you choose a different path, then they have different work. But enthalpy is a state function, so you can do that, calculate enthalpy, all right, based on only initial and final state. So this leads to a very useful law called Hess law. The Hess law says that enthalpy change of an overall process is the sum of the enthalpy change of its individual steps. And mathematically, it says the enthalpy change for overall reaction is the sum of the individual enthalpies added together. Okay, so enthalpy for a overall reaction can be calculated if enthalpy change for individual steps are known. Sample problem 6.9. Two pollutants that form in automobile exhaust are carbon monoxide and nitrogen monoxide. An environmental chemist must convert these pollutants to less harmful gas through the following reaction. Carbon monoxide, nitrogen monoxide react to form carbon dioxide and nitrogen gas. And we want to find the enthalpy change for this reaction. There are two reactions given here, A and B, that have known enthalpy change. So we want to use the Hess law, okay, combine these known reaction enthalpy changes to calculate a unknown reaction enthalpy change. So based on Hess law, we need to know known reaction, they start with the same reactants, they end up with the same product. So then we can calculate delta H by the sum of the individual enthalpy change. So do these two reactions start with the same reactants, end up with the same product? Well, if we look at A, you have a carbon monoxide, and that's the same reactants in the overall reaction. Now in the overall reaction, we have NO. So A doesn't have it, B have it, but in the opposite side, it's the product. So in order for the known reaction have the same reactants, we have to reverse B. So B, we need to write opposite. NO forms nitrogen plus oxygen. Now when we reverse the reaction, the enthalpy must also reverse. So now enthalpy becomes negative 180.6 kilojoule. So now do we start with the same reactants? Well, not yet, because in the overall reaction, the coefficient is 1. Here is 2. And therefore, we need to times half. And so by doing that, NO forms half nitrogen, half oxygen, and the delta H also needs to divide by 2. So that gives you negative 90.3 kilojoule. So the reaction B, by modification, we get a new reaction. And now if we add, so if this is B prime, we add A. Do we get the overall reaction? Okay, we'll see in the next slide. Here again shows the overall reaction. Enthalpy change needs to be calculated, and we have two known reactions with enthalpy change. And we just showed that B has to be reversed because NO in the opposite side and needs to times half. And so that's the new modified reaction. Okay, so now let's see if they start with the same reactants, end up with the same products. So we need to add these two together. Okay, so here is the A. Okay, reactants is CO, and here is modified B, and we have NO. Okay, now we still have a reactants oxygen, but we also have oxygen here. So they are the same reactants products, so they should cancel. And by doing that, we get a overall reaction that is exactly same as the one we want to find. They start with the same reactants, they end up with the same product, and therefore the delta H for this one should equal to the sum of the individual enthalpies according to Hess law. Note that you don't add these two, okay? Not these two, but by modified reaction enthalpy change. Okay, A is the same, B is different. Okay, it's negative 90.3 instead of 180. And by doing that, you add these two, And the answer is negative 373.3 kilojoule. In general, in order to calculate delta H for an overall process using Hess law, we first identify the target equation, the step whose delta H is unknown, and then we manipulate each equation with known delta H values so that the target amount of each substance is on the correct side of the equation. So in the last sample problem, we reverse equation B and also multiply by half so that they have the same reactants. So change the sign of delta H when you reverse an equation and multiply by amount and delta H by the same factor. Okay, and then add the manipulated equations and their resulting delta H values to get the target equation and its delta H. One application of Hess law is to use the standard enthalpy of formation to calculate the enthalpy change of a reaction. The standard enthalpy of formation, represented by change of enthalpy at the standard state, the formation, is defined as the enthalpy change for the formation equation from elements when all substances are in their standard state. The standard state is defined as 1 atmosphere pure substance in the most stable form. For example, the standard enthalpy of formation of sodium chloride is negative 411.1 kilojoule. According to the definition, this refers to the formation of sodium chloride from its elements. So sodium chloride, the elements are sodium and chlorine, and standard states are in 1 atmosphere pure substance in the most stable form. So the most stable form for sodium is just sodium solid, and the most stable form for chlorine is chlorine gas, Cl2. Instead of Cl atom, chlorine atom, it should be chlorine molecule. Okay, that's the most stable form. So the formation of sodium chloride refers to this equation, from sodium solid, chlorine molecule to form sodium chloride, and the enthalpy change for this reaction at the standard state is negative 411 kilojoule, and this is called standard. So this symbol represents the standard state, okay, standard enthalpy of formation of sodium chloride. Another example is the standard enthalpy of formation of ethanol. Okay, the formation enthalpy is negative 277.6 kilojoule, and this refers to the reaction to form ethanol from its elements. So elements has carbon, hydrogen, oxygen, and the most stable form for carbon is graphite. For hydrogen is H2, hydrogen molecule, and for oxygen is O2. Okay, so these all at the standard state, and when they combine, these elements combine, give you ethanol. The enthalpy change is called the standard enthalpy of formation. The standard enthalpy of formation for elements are always 0. For example, the standard formation enthalpy of carbon, okay, so carbon graphite, according to the definition, it shows the formation of a carbon graphite from its elements, which is carbon, and most stable form again is from graphite. So from graphite to become graphite, the delta H must be 0, and therefore the standard enthalpy of formation for elements are always 0. This table shows the selected standard enthalpies of formation at 25 Celsius. Note that the standard enthalpy of formation of elements bromine liquid is 0, calcium solid 0, graphite 0, mercury 0, nitrogen molecule 0. So for elements, okay, their standard formation enthalpy are zeros. Sample problem 6.10. Write a balanced formation equation for each of following and include the value of standard enthalpy of formation for A, silver chloride. So the formation reaction refers to the formation of silver chloride from its elements, which are silver and chlorine, and at the standard state, which means 1 atmosphere, pure substance, the most stable form. Silver, the most stable form is silver solid. Chlorine, the most stable form is chlorine gas, Cl2. Okay, so these add together to form silver chloride solid. Okay, and that reaction refers to the formation silver chloride, and we need to balance it, and we need to make sure it forms 1 mole of silver chloride. So silver is 1, chlorine should be half. Okay, and the delta H, the standard formation enthalpy, can be found from textbook, the appendix B. So here is the equation: silver half chlorine molecule forms silver chloride solid, and the standard enthalpy of formation equals negative 127 kilojoule. So the next one is calcium carbonate, and the formation of calcium carbonate is from its elements, which are calcium, carbon, oxygen, and the most stable form, calcium is solid, carbon is graphite, and oxygen is O2, and then you add all these together, okay, and balance it. So to balance this equation, oxygen needs to multiply by 3/2, and then we find the delta H from the appendix B, and so here is the reaction to form calcium carbonate from calcium, graphite, oxygen gas. Okay, the standard enthalpy of formation is negative 1206.9 kilojoule. Okay, next one, hydrogen cyanide. So this refers to the reaction from the elements which has hydrogen, and so here carbon and nitrogen. The most stable form, nitrogen, is O2, carbon is graphite. Okay, and you add all together, and you need to balance to make sure the product is 1 mole. All right, so nitrogen needs to multiply by half. Okay, so here is the balanced equation. So hydrogen also needs to multiply by half. So because product is 1, and then the value can be found from textbook. So how do we use the standard enthalpy of formation values to calculate the standard reaction enthalpy? Okay, suppose we have a reaction now from reactants to the products. Okay, and the enthalpy change from reactants to the products is at the standard state is the standard reaction enthalpy. So we want to find out, okay, this enthalpy change. So remember that reactants, so because products come from reactants, so they should have the same elements. For example, carbon monoxide react with oxygen forms carbon dioxide. Okay, so you can balance this one, and the product come from elements carbon, oxygen, and the reactants also carbon, so carbon and oxygen. Okay, because product come from reactants, so they should have the same elements. All right, so suppose reactants come from these elements, and the product also come from these same elements. And according to the definition of the standard enthalpy of formation, these elements combine to form the product. The enthalpy change at the standard state is called the standard enthalpy of formation of the product. And from elements to these reactants, the enthalpy change at the standard state is the standard enthalpy of formation of the reactants. Okay, so this is the formation enthalpy of product, and this is the formation enthalpy of the reactants, and this is the reaction enthalpy. And you can see the reaction enthalpy is the difference between these two. Okay, so we have the equation here. The standard reaction enthalpy is the difference between the standard enthalpy formation enthalpy of the product and the standard enthalpy formation enthalpy of the reactants. Okay, so it's the standard formation enthalpy of the product is this one minus standard enthalpy of the reactants, and that gives you the standard reaction enthalpy. Sample problem 6.11. Nitric acid is used to make many products, including fertilizers, dyes, and explosives. The first step in its production is the oxidation of ammonia. So ammonia reacts with oxygen, forms nitrogen monoxide and water. Calculate the standard reaction enthalpy from the standard formation enthalpy values. So according to the equation we derived in the last slide, the standard reaction enthalpy should equal to the standard formation enthalpy of the product minus standard formation enthalpy of the reactants. And we should look at the appendix B to find the standard formation enthalpy of product, water, nitrogen monoxide, and minus standard formation enthalpy of the reactants, ammonia and oxygen. Note in this equation, the M and the N represents the coefficient in the balanced equation. So M represents 4 and 6, and that means you should use 4 multiplied by the standard formation enthalpy of nitrogen monoxide plus 6 times standard formation enthalpy of water, and then minus N represents those coefficient of the reactants. So minus 4 multiplied by the standard formation enthalpy of ammonia minus 5 times standard enthalpy of formation of oxygen. So here is the calculation. The standard reaction enthalpy is 4 times standard formation enthalpy of NO plus 6 times standard formation enthalpy of water. So for NO from textbook is 90.3 kilojoule per mole. For water it's negative 241.8 kilojoule per mole. So don't forget the negative sign here. And then you minus the product added together. So you should add the product together. You minus both. Okay, and so minus, and then 4 times the standard formation enthalpy of ammonia, which is negative 45.9, and 5 times standard formation enthalpy of oxygen. So as we know, elements, their standard formation enthalpies are 0, so you times 0, and that will give you negative 906 kilojoule. So the standard reaction enthalpy is negative 906 kilojoule. What does negative mean? It means the reaction is exothermic. Okay, at the standard state, it releases this amount of heat.